If your company designs electronic systems, then understanding how to model and enhance the reliability of your products is essential to protect your brand and minimize costly field returns. My name is Ian Mosley, and in this short video I will outline some of the basics of reliability modeling and lifetime prediction of electronic systems. I'm also planning to write a white paper on this subject, so please indicate in the comments section below if you'd be interested in receiving a copy. Reliability prediction is based on statistical modelling of the failure rate of a product, i.e. how many units in a field population fail in a given time. This is modelled using the bathtub curve with the failure rate lambda plotted against time. And as you can see, lambda varies through a product lifetime. Just after manufacture, the failure rate is high due to infant mortality, with most manufacturers preventing these failures reaching the field by undertaking product burn-in. This prevents faulty units reaching the field in the first place. During normal operating life, lambda reaches a roughly constant level, which represents normal failure mechanisms. And at the end of life, lambda begins to increase due to wear-out effects of some components, and we will discuss some of the most common shortly. This increase in lambda indicates the normal useful life of the product. As an example, consider a product with a normal operating life lambda of 100. If we had 10,000 of these products operating in the field 24 hours a day, then over the course of a year of normal operating life, we would expect about 9 to fail. Lambda is related to the commonly used term known as mean time between failure, or MTBF. MTBF is often used on manufacturer datasheets as a reliability metric for a product and is often misunderstood. MTBF is not how long the product is going to operate for without failure. And in fact, after an amount of time equal to the MTBF, about 63% of the field population will have already failed. So components reach end of life in different ways. Electrolytic capacitor wear out is one of the most cited mechanisms whereby over time the electrolyte in the capacitor evaporates, causing a reduction in capacitance, increase in parasitic resistance and an increase in temperature dissipation. Also, in many components, thermal cycling will lead to repeated mechanical stress and fatigue if parts of the component or system have mismatched coefficients of thermal expansion. And nearly all wear-out mechanisms speed up as temperature is increased, and this can be described using the Arrhenius relationship, which predicts that the lifetime of a component decreases by a factor of 2 for every 10 degrees increase in operating temperature. But the most important aspect of high reliability design is to understand component wear-out mechanisms and measure operating stress levels, particularly temperature, on real hardware.